Okay, so let's start with a wild idea. What if I told you that in the world of computing, raw power isn't everything? What if a smarter approach could absolutely crush brute force, even when it's facing a massive hardware disadvantage? We're going to dive right into that.
So let's chew on this question for a second, because on the surface, it just sounds, well, it sounds impossible, right? Can a machine that is literally 1,000 times slower actually win a race against a top-of-the-line supercomputer? It sounds like a riddle, but the answer, you'll see, reveals one of the most fundamental truths in all of computer science.
All right, let's meet our competitors. In one corner, we have Computer A. This thing is an absolute beast. We're talking 10 billion instructions every single second. And in the other corner, Computer B, kind of chugging along at just 10 million instructions per second. Yep, it is 1,000 times slower. And the task for both of them is exactly the same. Sort a list of 10 million numbers. It's the classic tortoise and the hare story, but with a serious digital twist. Now, to understand how our little slowpoke even has a chance, we have to look past the hardware. The secret weapon here isn't in the silicon. It's all in the strategy. It's what we call the ultimate digital recipe, the algorithm. So what is an algorithm, really? I mean, the formal definition is right there. It's a procedure that takes an input, does some stuff, and produces an output. But let's just cut to the chase. An algorithm is simply a recipe. That's it. It's a specific, step-by-step guide a computer follows to solve a problem. And just like in cooking, the quality of that recipe can make a huge difference in how things turn out. And here's what that looks like in the real world. For our sorting problem, the input is just a big, jumbled mess of numbers. The output, that same list, but perfectly ordered, smallest to largest. The algorithm is the magic in the middle. It's the precise set of instructions that turns that chaos into order.
And that brings us to a really critical point. Not all recipes are created equal. Our two computers, they're running two very, very different sorting algorithms. And it turns out that how you sort is every bit as important as how fast you can do the sorting.
Okay, so our super-fast computer A, the hare, is using a method called insertion sort. This is the one that just makes sense. It's the approach you'd probably use if I handed you a mixed-up deck of cards. You'd pick up one card at a time and just slide it into its correct spot in the hand you're building. It's simple, it's logical, it's easy. But our slower computer D, the tortoise, is using a much cleverer strategy. It's called merge sorts. And this is a classic divide and conquer approach. So instead of trying to sort the whole giant list at once, it just keeps breaking the problem down into tinier and tinier pieces until it has a bunch of lists with just one item, which, hey, are already sorted. Then it cleverly starts merging those little sorted lists back together, step by step. It's way less intuitive, but it is way more strategic. So this stage is set. We've got the blazing fast hare with its simple, straightforward plan, and the slow but steady tortoise with its clever divide and conquer strategy. So let's see what happens when the race actually begins. And let's not forget the scale of this thing, 10 million numbers. See, for a simple algorithm, every single new number you add can make the problem much, much harder. This is where those tiny little differences in strategy start to matter. A lot. And here they are, the race results. Computer A, our supercomputer, the one running that simple insertion sort, took more than 5.5 hours to finish the job. Now, our slow computer B, the one that's 1,000 times weaker, it finished the exact same task in under 20 minutes. It didn't just win, it was over 17 times faster. No joke. Wait, what? How is that even possible? This just seems to defy all logic. How can 1,000 times disadvantage in pure speed be overcome so completely? How can a clever plan beat raw power so badly? Well, here's the secret, and it's so important. It's not about the initial speed. It's about the rate of growth. As the number of items, we'll call it n, gets bigger, the number of steps that insertion sort needs just explodes. It grows quadratically, or n squared. That means the workload doesn't just get bigger, it skyrockets. But for merge sort, the work grows in a log linear way, n log n. And that is a profoundly more efficient way for a problem to scale. It grows way more slowly and predictably. And this chart just shows it perfectly. Look at that bar for n squared. As the problem gets bigger, the time it takes just goes through the roof. It becomes totally unmanageable. Now, look at the bar for n log n. Yeah, it grows too, but in a much more controlled, graceful way. For really big problems, the smarter approach isn't just better, it's the only one that's actually possible.
This all leads to a really powerful realization, and it's summed up perfectly right here. An efficient algorithm is a form of technology. It's just as powerful, just as important as a faster computer chip. It's a tool that literally multiplies what we're capable of.
And believe me, this isn't just some fun little thought experiment. This principle, algorithmic efficiency, is the invisible engine that is driving so much of the modern world we rely on every single day. Every single time you use your GPS to find the shortest route, or you use a search engine to dig through billions of web pages in a blink of an eye, you are seeing the power of efficient algorithms at work. From keeping your credit card safe online to analyzing the entire human genome, these smart recipes are what turn computationally impossible problems into everyday realities.
So, the next time you hear about some big technological breakthrough, just remember, it might not be about faster hardware at all. The real revolution might just be a more elegant recipe, a more clever way of thinking about the problem. And that leaves us with this final thought. What are the huge challenges of our time that are just waiting, not for a faster machine, but for a much, much smarter algorithm?